Alright, let's have a look at problem 1011, capacity of ship packages within D-days. So for this problem, we are going to share again a binary search solution. And first, I'll go through the statement of the problem and look at the constraints. Then I'll explain the method and the main procedure and emphasize the importance of search range. Then we are going to share the code and do the tests. So first, let's look at the statement of the problem. So here we are given a conveyor belt which has packages that must be shipped from one port to another within these days. So let's call it D-days, aligned with the title. So the ith package on the conveyor belt has a weight of width I. So each day we load the ship with packages on the conveyor belt in the order given by the weights. We may not load more weight than the maximum weight capacity of the ship. So we are required to return the least weight capacity of the ship. That will result in all the packages on the conveyor belt being shipped within D-days. So that's the main statement of the problem. So let's look at the examples provided here. So in example 1, so the days is 5. So we want to finish the shipping in 5 days. So the cap is 15. And here in the explanation, it gives a strategy. So for example, in the first day, we ship the first 5 stuffs. So their total has weight 15, which is equal to the cap. So in the second day, they ship 6 and 7, which adds sum 13. Third day, we ship 8. Fourth day, we ship 9. And fifth day, we ship 10. So notice that we cannot combine the third day or fourth day because they add up to 17, which is larger than the cap of the ship. So this is example 1. And example 2, so the days is 3, the weights is given here, and the output be 6. So here is one strategy. First day, each day we ship 2 items. First day is the total weight of ship is 5. Second day is 6, and third day is 5 again. Similarly, in example 3, so the days is 4, and the output for the cap is 3. So with that said, let's look at the constraints. So the days is greater or equal than 1 and less or equal than the length of the weights. So here this one, if the days is greater or equal than the weights of the length, actually we can just take the gap as the maximum of the weights. And also another one is the length can up to 5 times 10 to the power order 4. So in other words, we cannot purely solve this problem by brute force. So the second constraint is about the range of the weights, right? So with that said, let's look at the method and the procedure. So sort of routine now, if we have look at problems like problem 410, problem 688, 68, and problem 2064. So here the method is binary search. What we want to do is as follows. First, we are going to define a boolean function. I will call this function f just for ease of writing. So given the cap, this function returns using the current cap in the argument if all the packages on the conveyor belt can be shipped within D-days. So this is the first step. So this boolean function actually produces order or monotonicity for below, and it also enables running the binary search procedure. In second step, we first reformulate the problem. So with the definition of f, we are going to transform this problem to a problem like we want to find the mean cap such that f cap is true. This is exactly the problem statement actually. So then we do binary search with the monotonicity produced by the boolean function f, and within proper search space. I will say proper. So this search space actually is very crucial. So here I will mark that crucial or important. So again, so the method here can be applied to problem 410, problem 668, and problem 2064. So it might be good to have a look at those problems. So let's now look at the code. First, I'm going to do the procedure step 1. So I write a boolean function. So this boolean function are going to check, given the current cap, if we can finish the shipping in the given days. So first, I'm going to make a net initialization count how many days we need, and also the subtotal, which is a current load within the day. So let's call it 0. So then we're going to iterate for the weights. So first we want to increment the subtotal. We can do this first because we initially set the subtotal to be 0. So we can add this W. Then we do the check. So if subtotal is greater than the current cap, means that this current weight we are looking at cannot be shipped with the previous weights in a single day. So then we are going to increment the count by 1. This count means we are going to ship this weight in this day, and all the previous weight are shipped in the day corresponding to the previous count. So with that side, we are going to reset the subtotal, right, to be W. So here actually we can do an early stopping or early check if the count is greater than days. So we are going to return false. So otherwise, after the loop, so we can finish the shipping. We just need to return true. And essentially, this function is doing the count if count is less or equal than days. So this is step 1. Now let's look at step 2. So reformulation and the binary search improper range, search range. So for this, first, a shape or a weight cannot be separated. So the lower bound of the cap will be maximum of the weights, and the upper bound, let's call it high, will be the sum of the weights. So if we consider we want to ship all the things in a single day, that's the high. So with that side, let's do the binary search. Let's initialize that. So the maximum of the height and the sum of the height. We're going to come back to this point later. So now let's do the while loop. While low is less than high, we're going to compute a temporal variable called mid, which is halfway in low and high. So if we use low as reference point, basically we want to walk to halfway. High minus low divided by 2, right? Integer division. Then we are going to do the check. If f mid is true, we are going to update the search space. If f mid is true, it means that using the mid as the cap, we can finish the shipment in D days. Then we will search for smaller, so the searching range will from low to current middle, right? So we want to set the high to mid. Notice that mid is still a possible cap, right? Because f mid is true. Otherwise, we cannot finish the ship in in D days using mid as cap. We're going to search above. So then this corresponding to set the low, but we need to set low to mid plus 1. The reason is made is invalid in this case. Or precisely, we cannot use made to finish the shipment in D days. So with that said, if we interpret the meaning of the high and low, we're going to return low as our result. So with that said, let's first do some cases check and then make some comments. So if we check, it passes the first one, and let's do the second check for days 3. So here cap is 6. So for this, that's okay. And so here we want to first check the generic case. So yeah, it passes the generic case. So now I guess it's time to make some comment about the range. So here the search range is optimal. So if we want to add the upper bound, say add some number, let's say 1000, it still works. So but we use more operations. So if, for example, yeah, this works. However, the lower bound cannot be lowered anymore. The reason is that we cannot split a weight. So let's do this. That's the -2. Then we check. It's still okay. Let's minus something big. 3. This example is going to be okay. Let's look at the first example. See. So this is a very subtle point. Let's minus the -2 for this one. Let's change to a smaller one. That's max 8. Let's see, 5 maybe. Just that's still okay. That's 1,000. Let's try another one. Let's see this one. Here days is 4. Let's write some -2. See. Yeah. So in this case, it gives a wrong answer due to the range of the search range problem. So if you because weight -2, so maximum -2 is 1, right? So but we only have 4 days. So if we do not do this, so it will work. But also we cannot add for sure. So if we add, we exclude the possibility. So overall, we want to emphasize that the proper search range actually is playing an important role here. So now I guess with that said, it's good to do a time complexity analysis. So for this problem, the time complexity analysis is sort of direct. So because here we do binary search in this range from low to high. So we do log times. So right. So the number of calls for the f is sum of the weights minus max of the weights, and then each time the function f actually is a linear function, right? So we traverse the weights, so it times the length of weights, so up to a constant, or we can use a big O constant. So that's the time complexity for this problem. I guess the video running long, so that's about it. Thank you very much.